Before starting the regular lectures of mechanics of materials, I feel that there should be a revision lecture. It is not from the textbook, but there are some basic concepts from engineering mechanics which I want to discuss before starting the topics of mechanics of materials. So I have named this lecture as revision of prerequisites for the course of mechanics of materials. You have already studied these topics and these concepts in your engineering mechanics course. So I will revise some of the basic concepts which will be used in this course of mechanics of materials. You can download my lectures, PDF slides and videos from my website, which is a Google site, sites.google.com/view/ATTA85, or from my YouTube. Okay, moving further. What is mechanics? You have already studied much about it, discussed about it. Mechanics is actually the study of mechanical interaction between two bodies or more than two bodies. Whenever two bodies are in contact with each other or they interact with each other, they exert different kind of forces on each other, different types of moments. The study of those forces and their effect, study of the effect of forces on the objects is called mechanics. And this course of mechanics is the foundation of most of the engineering sciences, and it is an indispensable prerequisite to their studies. Similarly, mechanics is a prerequisite to the mechanics of materials. Engineering mechanics is actually prerequisite to the mechanics of materials. Here are two examples have been given. For example, if a car is moving, it is pushing some force on the surrounding air, and then the air is exerting a reaction force on the car. Similarly, due to the weight of the car, it is putting some force on the ground, and the ground is applying a normal reaction force on the car. So force P and reaction force of the air. Similarly, weight of the car and reaction of the ground. So these forces and their reactions are actually studied in the course of engineering mechanics. Similarly, if we have a body with mass m1, this body, the mass always acts downward. So mass into g, gravity, acceleration due to gravity g. So there is a weight acting downward. This body is lying on a surface, so there will be a reaction force of the surface on the body, which is force N. The body is tied with a rope to another body of mass m2, so weight m2g. This rope is actually under tension. The rope is under tension between the two bodies m1 and m2. Remember that ropes are always under tension. Ropes are kind of members which are designed to bear tensile loads only. So this tension is actually not visible. We cannot see this tensile force, but we can imagine it when the rope is tied with the two masses and both are acting in different directions. So the rope is definitely trying to pull both of them in opposite directions, and the rope is under tension. So this tension is a reaction force. Weight is an acting force due to the bodies, and N normal is a reaction of the surface on body m1. So this study of these forces and their reaction forces is actually study of mechanics. What happens if we do not apply our knowledge of engineering mechanics properly? So it is very important to apply engineering mechanics, the equations and the laws of engineering mechanics whenever you design something as an engineer. Here is an example in front of you. An excavator is trying to lift some load, and you can see that it has lost its balance. It is because the laws of equilibrium have not been followed properly. In laws of equilibrium, we say that summation of forces must be equal to 0 in all directions, and summation of moments in all directions must be equal to 0 in all 3 dimensions. So in the given plane, we can see that the body has rotated counterclockwise. It means that the counterclockwise moments were more than the clockwise moments. That is why the body has rotated or disbalanced in the counterclockwise direction. So it cannot function properly because the laws of mechanics were not followed. Which law of mechanics? Law of equilibrium. So laws of equilibrium are very important in the subject of engineering mechanics, and similarly in the subject of mechanics of materials. So always remember to establish equilibrium whenever you are studying this course of mechanics of materials. What are the laws of equilibrium? In many applications of mechanics, the sum of the forces acting on a body is 0 and a state of equilibrium exists. Sum of the forces must be 0 and sum of the moments must be 0. In 3 dimensions, we have 3 forces. Forces in x direction, forces in y direction, forces in z directions. They all must be, summation of all of them must be individually equal to 0. Similarly, summation of moments about x-axis, summation of moments about y-axis, and summation of moments about z-axis must be equal to 0. Then only you can say that equilibrium exists. In 2 dimensions, we have 2 direction of forces. For example, if it is xy plane, so summation of fx and summation of fy both must be 0. And in 2 dimensions, we have only one moment, z must be 0. So body is in equilibrium if all the forces and moments applied to it are in balance, or if the resultant of all forces and moments acting on the body is 0. You can see an example in this figure. If the force is acting downward, the weight of the car and the upper lift on the car, if they are not equal, there will be no equilibrium in the vertical direction, and the car may fall or it may lift up against the desired position. Similarly, if it is not in balance, if the equilibrium if the moment in counterclockwise and clockwise directions are not same, so it will rotate and there will be no equilibrium, so the workers cannot do their work properly. So laws of equilibrium are very important to be followed in the studies of engineering mechanics and mechanics of materials especially. Mechanics can be divided into different types of or different branches actually: rigid bodies mechanics, deformable bodies mechanics, and fluid mechanics. So fluid mechanics is actually not our topic. You can study it as a different subject. Deformable bodies and rigid bodies both are solid bodies, so we will study solid bodies in this course. Rigid bodies are the bodies which offer negligible deformation under forces, under loads. Negligible means almost equal to 0. There is no deformation in a rigid body under force. So deformation means change in shape, change in geometry. We assume that there exist some bodies which do not offer any change in shape. It is actually an assumption. There is no such purely rigid body in the universe. So we assume some bodies which offer very negligible deformation, so we call them rigid bodies. Deformable bodies, they offer deformation. They can be elongated or they can be compressed, they can be rotated, they can be twisted. Volume can be increased or decreased under different types of pressures. So those bodies are called deformable bodies. Rigid bodies mechanics, you have already studied some topics related to rigid bodies mechanics in your course of engineering statics, where study of equilibrium between different bodies have been discussed, and we assume that acceleration of such bodies is 0. Either they are static or they are moving with constant velocity. So you have studied such bodies in engineering mechanics, where you have already studied external forces, not their internal effects. Similarly, in the subject of engineering dynamics, you have studied moment of bodies under different types of forces. But in this course, mechanics of materials, which is also mechanics of deformable bodies, you will study the internal effects of forces on bodies. Remember that mechanics of materials or deformable bodies mechanics is related to the internal effects of forces on bodies. The external effects have already been discussed in the course of engineering statics. So now we will discuss the internal effect. What is internal effect? Internal effect is deformation. Internal effect is stress, strain. So the changes in the body against external forces, internal changes in the body against external forces, or internal resistance of a body against external forces will be studied in the deformable bodies mechanics, and the course will be called mechanics of materials. Okay, previously you have studied about force. What is force? Force is the action of one body on another body, and it is a vector quantity. You know what is vector. So if there's a force is vector, it has a direction and magnitude. So we have studied a principle which is called principle of transmissibility. You have studied it in engineering statics. What is principle of transmissibility? In this figure you can see that the force P can be transferred within its line of action. So it has been transferred from point A to point B. Both the points are in the same line of action of the force. So force may be applied at any point on its given line of action without altering the resultant effects of the force external to the rigid body on which it acts. Okay, you have studied this principle in engineering statics. According to this principle, we can move a force within its line of action from one point to another point. It will not affect its external effects, external resultant. Okay, there's another theory, another law which is called force couple system. According to this theory or this law, you can transfer force from one point to another point offset of its line of action. There's a difference between these two theories, these two principles. In principle of transmissibility, you have to transmit the force within its line of action. But force couple system says, for example, if we move this force F from point A to point B, how can we move it? We have to draw a similar force at point B, F. If you are drawing a force F, you have to draw its opposite force minus F, so that they cancel out their effect. So this F minus F, the resultant will be 0 at point B. Okay, so now this force F and this force minus F have a perpendicular distance D. They are actually a couple. Similar forces with an offset distance D. They are producing a counterclockwise moment here in this diagram. So we can replace these two forces and the distance with a couple moment M, which is equal to force into distance D. So while this force at B, force F is at its own location. So the force at point A has been shifted to a force at point B, but it is now replaced with a force and a moment, which is equal to Ft. So this system is called force couple system. According to force couple system, a force can be replaced by an equal parallel force and a couple in the same plane. Remember that they should remain in the same plane. It is two-dimensional. This combination of a force and a couple is called force couple system. So according to principle of transmissibility, the force can only be transmitted within its line of action. According to force couple system, a force can be transferred out of its line of action, but then you have to replace it with a force of similar magnitude and a moment which will be equal to the product of the force and the distance between the 2 points, the perpendicular distance between the 2 points. It should remain in the same plane. Okay. Then another important topic is free body diagram, and we will continuously use this concept of free body diagram. So you must be an expert of it and you must understand it fully. What is free body diagram? Before that, we need to know that how can we isolate a system, a mechanical system, from its surrounding. A mechanical system is defined as a body or a group of bodies which can be conceptually isolated from all other bodies. For example, here we have a system. In this diagram, you can see a blue color member. A force P has been applied at it. It is fixed with the ground, pin connection at point B, and then it is resting at point A. There is a moment M applied at the other end. If we have to isolate it from the surrounding, so we can just draw in the other diagram, we can draw the same system without its surrounding. But after isolating the system from its surrounding, there are some points where the system was in contact with its surrounding bodies. So at those points of contact, we have to mention the reaction of the surrounding. At point B, there was a pin support. So we have to replace this pin with its reaction forces. So pin can be replaced with two reaction forces, horizontal and vertical. You have studied it in engineering statics, and I will discuss it again after a few slides. Okay. The body, if it has a mass, which cannot be neglected in some cases. So if a non-negligible mass exists, so the body's weight will act downward. So force W is equal to mg will act downward at its center of gravity, wherever it is. And then at point A, the body was resting. So we have removed the surrounding bodies. So at point A, we have to mention the reaction of the surrounding on the body. So after isolating the body from its surrounding bodies, the system from its surrounding bodies, so you have to actually mention the reactions of the surroundings on the body at the points of contact. So here it was point A, point B, and the weight of the system. So free body diagram is actually a diagrammatic representation of an isolated system, forces and reaction forces on the system, and applied forces will always remain same. For example, this force P will remain at the same location, moment M will remain at its original location. Okay, here some examples on the next slide, or maybe before examples we have to discuss some basic types of reaction forces, modeling of action of forces or reactions of forces. If we have a rope, for example, flexible cable, belt, chain, or rope. So ropes, cables, belts, chains, they are always under tensile force. So we have to replace them with a tension force. Tension means it will always act away from the body. If this is the body or the mechanical system, the force is acting away from it, not towards it. So tension force is always shown with a direction away from the body. Then if the cable is at an angle, definitely you have to show the angle. If the cable's weight is not negligible, the cable will not be straight, it will be curved, and then you have to show the tension as a tangent to this curve at the initial point, and definitely angle will be shown. If there are two smooth surfaces in contact with each other, definitely the contact between two forces, between two bodies is always a kind of compressive force. So we have to show, if we remove surrounding of the body from the surrounding bodies from the system, we have to show the reaction, which is actually always a normal force towards the body, but it will be compressive. Remember that contact force is always compressive, so it will be towards the body. This arrowhead is towards the body, so it is compressive. Towards the body means compressive force, away from the body is tensile force. If the two contacting surfaces are rough, previously we have discussed smooth surfaces. If the surfaces are rough, definitely there is a friction force between them. So besides this normal force which exists, there will be a friction force also. So you can also show a resultant of these two, which is R. Either you show force F and N or resultant R. So two frictional for rough surfaces if there are two rough surfaces, so there will be a normal force and a friction force as reaction force in the free body diagram. Okay, if you have a roller support or a rocker support or a wheel support, definitely the wheel or the roller can move in one of the direction. So its movement is not restricted in horizontal direction in this diagram, but it cannot move in the vertical direction. So definitely there is a vertical resistance here. In whichever direction the moment is stopped or restricted, there will be a reaction force. So roller supports are not restricted in one of the direction. In this case, in the horizontal direction, they are not restricted. So definitely in the vertical direction, there is a reaction force. So roller supports, rocker supports, or ball support transmit compressive force normal to the supporting surfaces. Whenever there is contact, there will be compressive force, remember. Freely sliding guides, for example, this one, it can slide in the horizontal direction. This one, it can slide in the horizontal direction. But definitely, it is fixed in the vertical direction. It is fixed in the vertical direction. It cannot move up and down. It can move in right and left directions. So definitely, collar or slider guides, they are free to move along smooth guides in the horizontal direction. In this figure, it is horizontal. In some other figures, it can be vertical. So it can support force normal to the guide only. So there will be normal force which will be compressive again. Similarly, if there is a pin connection, you can see the pin cannot move in horizontal direction. It cannot move in vertical direction. It is fixed in horizontal and vertical directions. There is no transmission at this point in vertical or horizontal direction, but definitely it can rotate. Rotation is free. So there are only two resistance or two constraints, force in x direction or force in y direction, or you can replace it with a resultant of the two, which will be a resultant, and an angle will be there, theta. If the pin is fixed, usually the pins are not fixed, they are free to turn. But if a pin is not free to turn, this is a special case, it must be mentioned whenever if it is not free to turn, then there will be a moment resistance as well, moment constraint as well. So moment reaction will exist, but it is not a general case. Generally, if a pin connection is given to you, it is definitely free to turn unless it is mentioned that the pin is not free to turn. Okay, a built-in or fixed support or a weld support, definitely they are fixed. They cannot move in horizontal direction, vertical direction, or there is no rotation. So definitely there will be a vertical reaction, a horizontal reaction, and a moment reaction for fixed joints or welded joints or built-in joints. Okay, there are some exercises. For example, okay, now before that, if there's a body with mass always acts downward, so we have to replace it with a force W equal to mass into G. G is 9.8 meter per second square, and it will always act at the center of gravity of the body. Similarly, if there is a spring can be compressive or tensile. So if it is a compressive spring, or if it is under compression load, so it will be there will be a compressive reaction force. If the spring is under tension, or if it is a tensile spring, definitely there will be a tensile reaction force. So if it is a tensile reaction, definitely it will act away from the body. If it was then compressive, definitely the force will act towards the body. Springs are similar to ropes. They either support tension or compression. There may be coil springs, which we are not discussed at this moment. Coil springs can offer rotational moment as well. Okay, rotational supports as well. Okay. We have some examples here related to free body diagrams. If there's a plain truss and weight of the truss is negligible, in this first case, this force P is acting at its position. We have to just draw the outer boundary of the system. So outer boundary of system has been drawn in this diagram. At point A, there's a pin support. It has not been mentioned that the pin is fixed, so definitely the pin is free to turn. We have to draw two reaction forces, horizontal and vertical reaction. At point B, there is a rocker support, so there will be a vertical reaction force, compressive reaction force. Remember, if you mention wrong direction of the force, for example, if this force AX, you have mentioned it towards the left side, If it is wrong, after calculations, the value will be negative and you have to change the direction. If after calculations, numerical calculations, the force value is positive, it means your assumed direction was correct. So you can draw the force in any direction, either vertical, the horizontal forces in right or left direction, or vertical force in upper or downward direction. So you must know the direction, the axis, the vertical axis or the horizontal axis. But direction can be altered, it can be right or left, or it can be up and down. So you cannot draw a vertical force as horizontal force, but you can draw a vertical force either upward or downward. After calculations, you may know that your assumed direction was right or wrong. You can guess it from the sign of the force. The negative sign means your assumption was wrong, and the positive sign means your assumption was right. Okay, in the second case, there is a cantilever beam. It is under three forces, F1, F2, and F3, and then it is fixed at point A. And then there is a mass M. So due to mass M, there will be weight equal to mg at fixed end A. Fixed means there will be three reactions, two reaction forces and one moment. Similarly, another example is here. A beam, smooth surface at point A and mass M. There is a pin connection at point B. So point B, pin connection has been replaced with two reaction forces. Mass M means there is a weight W at center of gravity G, which can be determined. And at point A, there was a smooth surface. So smooth surface, it has been defined here. Smooth surface means a normal reaction force towards the body. In this example number 4, a rigid system of interconnected bodies analyzed as a single unit. If it is analyzed as a single unit, you can draw the outer boundaries here. At point A, there is a roller support, so there will be a vertical reaction force. At point B, there is a pin support, so pin support means two reaction forces, vertical and horizontal. This mass M is acting downward, so it has been replaced with a downward force equal to mg, and then this force B exists at its own position. Moving further, there are some exercises. Some incomplete free body diagrams have been given in the last column and you have to complete them. A bell crank, this is example 1, a bell crank supporting mass M with pin joint at A, pin support at A. There is a flexible cable, it has been replaced with tensile force T. The mass M has been replaced with a downward weight mg. And then at point A, there is a pin support, so definitely it must be replaced with two reaction forces AX and AY. It was missing in the diagram. Similarly, in the example number 2, exercise number 2, there is a control lever applying torque to shaft at O, at point O. And then there is a pull P. Pull P has been shown. Point O is actually kind of pin connection, so definitely there will be horizontal force. Then later on, definitely this horizontal force OX will be 0 because there is no other horizontal force. Summation of forces in horizontal direction is 0, so definitely OX will be 0, but in the diagram you have to show it initially for your understanding. Okay. Again, we have another exercise number 4. Uniform crate of mass M leaning against smooth vertical wall and supported on a rough horizontal surface. Vertical wall is smooth, horizontal surface is rough. So smooth surface means there is a normal reaction force at point A. Horizontal surface means there should be a friction as well. So normal force at point B is already shown. What is missing is a friction force Bx. It was missing in this diagram. And definitely if mass is given, so weight mg is there. Okay, this, okay, number 3, this was actually number 3 and this number 4. Okay, uniform pole of mass m being hoisted into position by which horizontal supporting surface notched to prevent slipping of pole. Okay, this pole is being supported by a rope, so we have replaced the rope with tensile force. Then if it is a mass m, so definitely at center of gravity, which we can find later, there will be a mass acting downward, and at notch point there is an upward force, normal force R, but notch is actually a rough surface, so we have to add a friction force here. We have to give it, for example, it is Rx, this one is Ry. It was missing. Some students always confuse it, like they will consider it as a pin connection and then they will add two reaction forces here. I have observed it in my previous few years. So if this is your system, mechanical system, you have isolated it, it was in contact with the rope at this point. You have already applied a tensile force T here. The mechanical system, our mechanical system, is not in contact with this point directly, so you do not need to apply two reaction forces here. This is wrong. So only its point of contact was with the rope and with the ground. So we have applied reaction forces at the rope point and the ground point. So similarly, you can attempt more exercises regarding free body diagrams in your book of engineering mechanics or engineering statics, which you have already studied as a prerequisite subject for the subject of mechanics of materials. So I request you to practice more and more problems, draw more and more free body diagrams. If you can draw kind of 50 to 100 diagrams correctly, definitely your concepts are clear. So please try to draw more free body diagrams of different systems and try to clarify your concepts regarding free body diagrams. From the next lecture onward, we will start the topics of mechanics of materials, where the free body diagrams are very important. Similarly, equations of equilibrium are very important. Understanding of force and its reactions are very important. So please revise your basic concepts. If you do not revise your basic concepts, it will be very difficult to understand the topics of mechanics of materials. So please revise your basic understandings of engineering statics. It is very important. So I think these topics were enough for you. If there's any point to discuss, if you have any query, any question, you can send me an email. Please send emails only, so I can answer you for your queries. You can also download these video lectures from the Google site, which I have mentioned in the beginning of this lecture, or from YouTube, and you can discuss with me any query related to these topics.